While headlines celebrate a battery revolution, the true crisis for electric vehicles lies beneath the pavement in our power grids. We are told range anxiety is the final frontier, but physics dictates otherwise. The real bottleneck has shifted from the car to the building and the substation. When adoption hits critical mass, we face a hard wall of thermal limits and grid capacity that no software update can fix. Today, we follow the engineering failure points where power density meets physical reality. The narrative often focuses on chemistry, how much energy fits in a pack or how fast it charges. But consider the numbers driving this shift. EVs now account for approximately 22 to 25% of new passenger vehicle sales globally. In Norway, that figure has exploded to 97%. In China, 53% of all new cars sold are electric. These statistics represent exponential growth where global sales double every 15 months. Yet, this acceleration exposes a severe supply-side constraint hidden in plain sight. The physics of electricity distribution dictates that rapid charging at scale requires massive substation upgrades and localized generation capacity that current building grids simply cannot support. As we move from early adopters to the mass market, the limiting factor is no longer how far a car can drive on a single charge. It becomes whether the local transformer in your neighborhood has enough headroom to handle thousands of vehicles plugging in simultaneously without destabilizing the entire grid. This creates a fundamental production trade-off where vehicle manufacturing outpaces infrastructure deployment by years. The core issue lies in the physics of simultaneous charging, which triggers what engineers call a superposition effect. Demand does not scale linearly with adoption. If you reach 50% EV penetration in a neighborhood without upgrading the local transformer capacity, you do not need just half again as much power. You require 3 to 5 times the existing capacity. This non-linear scaling happens because peak demand is driven by human behavior patterns. Everyone coming home from work at 6:30 p.m. and plugging their cars into identical circuits designed for lighting and refrigeration loads in a building constructed decades ago. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. High-penetration markets like Norway and China demonstrate that vehicle sales are rapidly decoupling from grid readiness. This creates what looks like a tragedy of the commons where individual rational charging behavior forces utility-level brownouts or necessitates expensive infrastructure retrofits. When one household plugs in, it is manageable. When an entire street does so at once, the thermal limits of local transformers are exceeded. The copper windings overheat, insulation degrades, and protection systems trip to prevent fires, cutting power to everyone on that block just as their vehicles need energy most. This constraint reveals a stark engineering reality. We can build cars faster than we can dig trenches for new cables or swap out heavy iron transformers in dense urban environments. The bottleneck is not the battery chemistry race, it is the physical layer of electrical distribution. Every kilowatt-hour delivered to an EV must pass through aging infrastructure designed for a fraction of that load. In many regions, the substation headroom has been exhausted long before the last car hits the road. Regional variance adds another layer of complexity to this engineering puzzle. While China and Europe lead in adoption rates, the United States accounts for only 10% of global EV sales. This indicates that grid constraints are not yet a universal bottleneck everywhere. In areas with lower penetration or newer distribution networks, the problem remains theoretical rather than acute. However, as targets push for massive electrification by 2031 across Europe and China, this gap will close rapidly. The knowledge regarding precise timelines for infrastructure overhauls is currently missing from public discourse, yet the physical requirements are absolute. You cannot cheat thermodynamics or magnetic saturation in a transformer core. The solution requires rethinking how we approach power density at the building level. It involves moving beyond simple plug-in chargers to integrated systems that manage load dynamically. We need substations with active cooling and modular expansion capabilities built directly into residential zones, not just industrial parks. This shifts the engineering challenge from optimizing cell chemistry in a factory to managing heat dissipation and magnetic flux across thousands of connected nodes simultaneously. Investors and consumers often miss these critical failure points because they focus on spec sheets rather than supply chains. The race is no longer about who can make a battery with higher energy density first. It is about who can deploy the grid infrastructure fast enough to absorb that power without collapsing local voltage stability. Until we address the physics of building grids and substations, every new car sold adds weight to an already overloaded system waiting for its breaking point. The engineering story behind this transition is one of physical limits meeting human ambition. We have solved the problem of how to move energy in a battery. The harder challenge remains moving that energy from the source through copper wires and iron cores into thousands of homes without melting them down. This is the next great test for our infrastructure, demanding a level of coordination between vehicle manufacturers, utilities, and urban planners that we have never attempted before. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.